how do you test the insert at the end?
I can pull up my my test suite if you want.
Because I had tested that and then I went back and tested it after you created it, and it works for me.
So how do I do this? So if I run this, this is just my test suite. So inserted head, inserted tail, insert in the middle, testing remove. So far so good. Oh, I think I even looked at yours and figured out why it was doing that. But essentially, when I added 3 at the tail here, it added 2 copies of 3. So maybe, did I say it was, what did I say was wrong with it?
That's what you said it was.
Yeah.
But like, I wonder.
I think I even looked at it and figured out, oh, yeah, I know, I see that. But if you can't figure it out, let me know. I'll look at it again. Okay. But yeah, I just, I mean, if you want to look at the this is the, you can probably kind of imagine what it is. I just call your member functions and do stuff. And of course, when you're dealing with linked lists, weird things can happen at the head and the tail. And then, so I test head and tail and in between and do weird stuff. And, okay. And I'll try to, like I said, I'll try to get my test suite to you. The problem is I usually kind of write these heading right into the last day when it's due, just because I don't have that much, you know, I don't know, procrastination, I suppose, more than anything.
You don't know anything about that.
Exactly. And but I'll try to get my test suite done maybe on Saturday so I can ship it out to you guys and link it. You can link against my test suite for your stacks. Speaking of stacks, let me show you. Let me talk a little bit about stack.
Technology advisory thing?
Exactly. Not even close. All right.
Oh, you are.
So here's just, you know, I wrote the stack stuff this morning, and then here was just me testing various things, making sure that I could push stuff onto the stack, making sure that I could do an assignment, right? I need an assignment operator overload to do that. And then what I do is I push some more stuff onto T, and then make sure that T and S have maintained their independence, right? That's kind of the classic problem with assigning dynamic memory objects to each other. I think this, yeah, I have to make it first. Yeah, so there's not much going on here, but there's T, -1, 2, 4, 2, 6, 4, 2, and then 2, 6, 4, 2. So T has the -1 on it, and S doesn't. This is the kind of stuff you want to do when you're really exercising your class, just to make sure that everything, literally everything, works. Notice, let me get rid of some of this stuff here, and let's just look at S. So pay close attention here. That's 2, 6, 4, 2, and the pushes are 2, 4, 6, 2. So does everybody see why the order is reversed? Because I push all these things on. By the time I get down to here, this first element is way down at the bottom of the stack. This is the top element, and then what do? I empty the stack by just pulling stuff off the top and popping. So you do top, pop until the thing is empty. And that's going to pull things off in the reverse order of how they were put on there. All right. Today what I wanted to do is talk about some of the implementations of the stack program, and in particular, as I was kind of surfing around and reading different sources about stacks, I was reminded of something. If you look at the stack header here that you guys are working with, I was reminded of something that I had promised myself I was going to use this semester, and I'm glad I caught it, because if you look down there, first of all, this time we're using a proper node class instead of a struct. So in the linked list exercise, you guys were using a struct that had some data and a next pointer in it. Now we've promoted the node struct up to a class, and once you have a class, then you've got you have to provide some way of accessing the class variables and changing the class variables. And I was really attracted to this the first time I saw it, where so the class data is simply a variable to hold data and another variable to hold a link to the next node. And the link is just a node star, and the data is some list item data type, and in this case we've got it typed def to int. What's interesting about this class is not the class data, but the public member functions. You've got your standard constructor, you've got an overloaded constructor that takes two arguments, a list item and a node star. That's for not only declaring a node, but actually setting the data and the next pointer, the link pointer, at the same time. And then here's where it gets interesting. There's a link member function that returns the link variable by reference, and there is the data function that returns the data variable by reference. What's really cool about this is if you use it on the right hand side of an assignment, it'll pull the data out and it'll be on the right hand side, and then you can take the data and assign it to some variable. That's wonderful. If you use it on the left hand side, and this is where it gets really weird, if I use the link function on the left hand side, it turns into essentially the data variable. Sorry, it turns into the link variable, and I can assign to it. It's really bizarre, but it's really slick, and that's what I'm going to talk about today. So,
I have a question about the second member function.
Yes.
Are we supposed to set the link to null or to the node?
The node pointer. So there are two arguments here. Yes, that's a bad comment. Thank you. Set link to. In fact, let me change the order here.
Do you want a separate, when we eventually work on it, do you want a separate .ccp file for each of the stack and node?
No.
Okay.
Ben, that question, do you want node to be in a separate file? The answer is no. I want them both to be in the same file, because node is never used anywhere else other than by the stack class. In fact, the way that this node class is designed, it would be dangerous to put it out in the open, because when you're returning links by reference and data by reference, what you're letting the user do is actually get at the contents of a node directly, and that's not something that you want to do, because you could break the stack. Right? The stack is built up of a linked list. If somehow the user can get in there and grab one of those nodes, that's bad, because they could break the stack. So I've hinted at something unusual about these return by references. I promise to clarify as we go through today. What I want to do is first start out by talking about the stack class. I want to talk about it member by member function, starting with the simple members and then getting on to the dynamic memory stuff like the copy constructor, the assignment operator overload, and the destructor. So let's start by talking about the simple ones first. What do I mean by the simple ones? I just mean from here down: empty, size, top, push, and pop. I'm going to leave that there, and then let's go to notes and just talk about each of these in turn. Again, I apologize if you guys have already downloaded stack.h. I've made some tweaks today. For example, this morning as I was working on it, I realized that I had named this variable size, and then I also have this member function called size, and that was a bad thing. And so I changed the member variable name to num elements, which is somewhat more descriptive. It wouldn't let me do it. Yeah, so I don't know if I was surprised or not. I don't know if I'd ever run into that before, but because you could certainly overload different symbols, but whatever. It's fine. It's probably not good practice anyway. So anyway, if you've downloaded stack.h, say yesterday, you should probably look at it again today. All right. So let's talk about a few of these simpler ones. First one is empty, right? So empty. What do you want to do with empty?
See if the top pointer points to that. Or all sides and see the size.
Yeah, you actually have two signals that you can choose from, right? If the head pointer is null, then it's an empty stack, or if num elements is 0, it's an empty stack. I'm almost pretty much 50-50 split on that. So you could either do, you could check head equal null, or you could check num elements equals 0. And of course you want to return true if if one of those conditions is true and false otherwise. That's an easy one. Okay, what's the next one here? Empty. Size. We're building our way up.
Return the number of elements.
Yep, doesn't get any easier than that. All right, next one. Top. I should check my comment there.
So like,
Yeah, so top, what's top going to do?
Reads off the top.
Yeah, how's it going to work?
You just look at it, right? What is the value that head points to, and you return the value.
Careful, not what the value the head, what kind of what the value the head points to.
Pointer, little arrow thing, number. If head's not equal.
Good point. Check empty first. Whenever you dereference a pointer, you should always think about, could this pointer be null? Always think about that. God, why do I want? It's a good rule of thumb. Whenever you have a dereference, ask yourself, might I be dereferencing the null pointer? Because that's a really short trip to a segfault. That's automatic. Okay, moving right along. Hey, we get interesting finally. Push.
Speaking of segfaults, so I noticed when I was writing my list class that if you get a segmentation fault, it's not always C-outing everything that you would put before the segmentation fault. Why / is there a good way to debug a program to find out if it's
cout, I'm not sure. I think this works. First of all, cout is a buffered operation. So it doesn't have direct access to the screen. What it does is it makes requests to the operating system to print things to the screen, and the operating system will say, yeah, I'll do that when I'm good and ready. And sometimes it's made the request, there's a request pending, but your program crashes before that pending request is actually executed. One thing that might work, but even this doesn't always work, is use the .flush member function, cout.flush, and what that does is it empties the queue of requests. I think there's a queue for cout, and then there's maybe a queue in the operating system that you're also fighting with, and so you might be flushing it, and then the thing quits, the process dies, and the operating system says, I don't need to do that. So I think it's still an iffy proposition, but it certainly sort of gets you one step closer. Push. So here we are adding a node at the head. All right, let's draw a picture. So we've got head here. Let's start with the generic case where we actually have something in the list already. What do? You create a new node. The new node points here, and then you have to update the head pointer, right? So a really quick way of doing this is something like temp equals new node and then whatever the new piece of data is, let's just call it X, and then head. And then head equals temp. Good. So that's using my 2-argument node constructor. The piece of data is the thing that you're pushing onto the stack, whatever that is. I'm calling it _x. And head is, this guy is going at the head, so head needs to point at this new node. And the new node actually points at the old head. And all of your adding, so the stack is much nicer than the general linked list. Everything that you put onto a stack goes on at the top and is always done by this operation. I guess we should ask ourselves whether this is okay with a null pointer, where with an empty list. Yeah, head comes in as null. We create a new node, and the link in that new node is now null, which is good, right? Because that's indicating the end of a list. So this is really nice. Yeah. Questions about push? Yeah.
How would we set what new node points to? Oh, because we declared head in the function. Okay.
Yeah, head is a member variable, and temp is just some temporary node star. Pop. Oh, and I guess one thing. What else should we do with push? Yes. All right, pop. Now, our version of pop is void, so it doesn't need to return anything. All it needs to do is remove the top element from the stack. So let's draw a picture again. H pointing to a node, which may point at another node, etc. What do you want to do? I want to get rid of this guy. So we want to get rid of that guy and make H point to the next guy.
Pointing to the first data element and then set head equal to pointer. First
Yeah.
Yeah, don't forget to delete, otherwise you've got a memory leak. Okay, so got to think about the order now here so we don't lose anything.
We'll need a temp, probably.
Yeah, we're going to need a temp. And where's temp going to... Okay, good. Okay, delete head.
And we don't have the X. Yeah.
Yeah, you need the next.
Head equals 10.
Sorry about that. Say it again.
Head equals temp arrow. I don't know. Next.
Oops, arrow.
Wait.
Okay. And now what? Yes. And finally,
Number minus.
yeah. So pictorially here, temp equals head. So now temp is also pointing here. Then head equals head link. There's that guy. Then delete temp. And decrement number of elements.
Advantage of using a link function just to make it.
So why do we have to use this function rather than essentially it's what's the word? It's I think in this case it's really just tradition in a sense, right? I could make a class with public data and public node star. And then I could just throw these things around directly using the dot operator or the dereference operator, whichever. But the tradition in C++ is that you stick all of the data, all of the member, all the class variables in the private section, and then you access them through functions. And so that's why we're using the functions here.
Oh, so basically, since it's a class instead of a structure,
Right.
you
You can't just go. The tradition is to not go straight in and muck around with the class data.
even though.
It's such a simple class, you could.
Well, and that's functionally what you're doing.
Yes.
It's not too much of attention.
Okay. Now, if you had implemented these 1, 2, 3, 4, 5 functions, you would have stacks that generally worked. The only thing that you would be missing is you wouldn't be able to pass them to a function by value, and you wouldn't be able to assign them to each other. But you would have stacks that could keep track of numbers, and as long as you didn't mix them in the ways that I just described, you'd be fine. What we want to do now is talk about the memory, the dynamic memory aspect. So the dynamic memory components of this, I'll repeat, are the destructor, the assignment operator overload, and the copy constructor. And let's talk about each of these guys in turn. The destructor. A couple different ways you could go about this. And you may assume that we've written all the functions above.
Can't you just pop everything?
I can pop until empty, right? So we could do that. Because we were careful with pop, pop deallocates nodes, and so you could just pop until empty. But of course, deleting a linked list isn't that much work just to traverse the list, right? So if you want, you can traverse the list.
In what kind of situation is there a significant cost to implement a function like that?
We were doing million element lists or whatever.
I think that's an excellent question, and the short answer is I don't know. Compilers have gotten so good at optimizing themselves, right? So how many of you guys have heard of optimization, compiler optimization? Some of you. So you compile your code, and you can actually set these different levels of optimization. And what optimizing compilers do is they actually analyze your code and they rewrite it in ways that's more efficient before it gets compiled into the binary. And your question really gets to the heart of whether the optimizer is going to catch that and fix it for you. I think if you pop until empty and the compiler leaves it alone and lets you just pop until empty, I suspect that that's going to be a little slower than a list traversal. But I also suspect that if you turn on the optimizer, it's going to see that and make it slicker than that. And so I don't know the answer, and I suspect that it's really in the margins, really a small difference.
Coding that sort of stuff must be terrifying.
Coding optimizers? Yeah. I mean, it's really where the money is in compiler design right now. Is who's got the best optimizers? Who can produce the most highly optimized code? And optimization is really a fascinating field because it's sort of gone through a renaissance in the last 10 to 15 years with the development of multi-core processors and massively parallel machines. Because the holy grail of optimization is to take a program that some idiotic programmer like me writes and then recognize that I'm going to run it on a machine with n processors and take my code and parallelize it. It's a really hard problem. There are compilers out there that'll look at your loop, and they'll see that the loop is essentially each step of the loop is somewhat independent, and it'll automatically parallelize that, dump that onto distributed across several processors. So optimizers are getting good, and they're, that's just the simplest possible case. They're just ridiculously complicated algorithms for automatically parallelizing code, and that's really where most of the compiler design work is being done right now, to automate parallelization. Okay, so we've got this destructor, and we can pop until empty, or we can traverse the list and deallocate as we go. And you're familiar with that because your destructor for the linked list class essentially traversed the list and deallocated as it went. Although I suppose your destructor could have also just successively removed the first element. So maybe you did that. Moving right along, here's the biggie of the day. Let me just make sure I've got, let's talk about the assignment operator overload. Okay, so you have the boilerplate stuff, the self-assignment check. And you remember how to do that. If this equals the right-hand side address, then just return. Just return this. Similarly, clear out the left-hand side. Also relatively straightforward. How might we clear out the left-hand side? You can't invoke the constructor explicitly, but you can do what the destructor is doing. So you essentially want to do what the destructor is doing, which is either pop until empty or traverse and deallocate. So we clear out the left-hand side by either pop until empty or traverse. How about, okay, and then the other thing is you clear out the left-hand side. Let me just note here that it's really important that you set head equal to null and num elements to 0.
Does RHS have these movements?
Right-hand side. I'm just referring to the notation that I used on Monday, where the argument to the assignment operator is the right-hand side, and then the this operator, the this pointer is referring to the left-hand side. So when I say LHS, what I'm really talking about is this. I'll make a note of that here. So the left-hand side is this. So you clear out the left-hand side, which means you remove and deallocate all of the nodes in the linked list. You set the head pointer to null and the number of elements to 0. Now we need to repopulate. We need to copy the RHS to LHS. How might we do this? How about if I just pop everything off of RHS and push it onto LHS? I need to maintain the order. So it would be so nice if I could do that, but I can't. And in fact, there's a couple of problems with that. The way that our stacks are defined, popping, I cannot get past the top element of the stack without losing the top element of the stack. Does everybody see that? At least using the class itself, I can't get to the third element in the stack without popping the first and the second element, and then they're gone and I've destroyed the right-hand side. So taking the right-hand side and popping, doing top pop into the left-hand side, I'm going to populate the left-hand side and I'm going to deplete the right-hand side, which I don't want to do. I'm not even allowed to do because I'm passing it in by constant reference. And I'm going to reverse the order of the elements. So two serious strikes against that approach.
About creating a dynamic array and then just shoving all of it into a dynamic array and then shoving it.
So if memory is not an issue, right, you could create a third-party array, and you still really can't do it without damaging the right-hand side, though.
I mean, you would just need to be careful about which order. Well, because you take everything out of the right-hand side, so they're both empty, and then you put it back into both of them at the same time.
But remember that the right-hand side is a constant reference. It's a constant stack reference, so I'm not allowed to change it. And pop is going to be seen as changing, which it rightly does, changing the stack, and the class structure is not going to let me call pop on the right-hand side. Yes?
Can you just set the left-hand side head to the right-hand side head?
That's exactly what we don't want to do. No, I not to be flippant, right? But what that does is it gets the data in the stack tangled up between two different objects.
Right.
So what we have to do is do this the hard way. We have to copy the linked list.
You have to traverse the list.
You have to traverse the list. You have to start at the right-hand side head pointer and go through, allocate a node, copy the node over, advance the pointer through the right-hand side, allocate a new node, copy the data over, advance the pointer, allocate a new node, copy it over until you get to the end of the list. There's no way around it. And that preserves the order of the stack. So there's no way around it other than, let me get me a head pointer here.
So the copy constructor would have a similar setup then, right?
Well, copy, once you get assignment written, copy is easy.
Okay. Yeah.
So yes, it does.
So yeah.
So we start out with the left-hand side is pointing at 0 and the right-hand side is presumably pointing at some list. And you get your cursor. And you get temp, which is a new node. This temp guy will just set its pointer to null, and we'll copy the data out of that guy and into that guy. And there's one case. If head is null, then we set head equal to temp. And then otherwise, we just update the pointer accordingly. You're going to need a prev pointer here. Oops, I did that in red. So when we start out, prev is going to be pointing at 0 as well. Temp is going to be pointing at the new node. So if this is the first node, then just let h equal temp.
0 is null.
Yep. If it's not the first node, let's say we make a new node. Temp now points at the new node. Previous now points at this guy. copy the data over. And then just make, when you're done, make prev equal to temp, and temp equal to a new node, and just keep doing that. Prev equals temp, temp equals new node, prev equals temp, temp equals new node, and moving that down, and that will generate the new list. Let me just check my. I want to see if I did what I was talking about. So let me just return and talk about this return by reference stuff. What becomes possible with return by reference is, let's say that we want to set head to some value. This is something that you've never seen before, I suspect. So head is a node pointer, and head arrow data invokes the data function in that node pointer, in that node, excuse me. Data is a return by reference. So what it does is it returns essentially a not a copy, it returns the original piece of data from that node to the left-hand side. And then I do an assignment to it. And because it's the actual piece of data, not a copy of it, but the actual piece of data from the node, when I do the assignment, that piece of data gets overwritten by X. So when I return by reference, what appears there is the actual data, and then I assign to it, and I move on, and that's a way of modifying that particular node, the head node. And I can do the same thing with the link node. Right? So if I say have allocated a new node and temp is pointing at the new node, I can do head link, and that returns not a copy of the address, but the actual pointer that's sitting inside that node, and then I assign a new value to it using temp. Similarly, I can use these in the other direction. Let's say I simply want to get data out of the stack. Okay, so here you again reach into the head node and you pull out the actual honest-to-God piece of information, the original piece of data, and it sits there on the right-hand side. Then, if necessary, that equal sign might invoke some assignment operator overload for some really sophisticated class of data, and it'll take that original piece of information, make a copy of it, and stick it into X. So it won't take the original piece of data and put it on top of X and hopelessly kind of intertwine those two guys. Assignment will take over. It'll take that right-hand side original, it'll make a copy, and put it in the left-hand side, just like assignment always does. That's what assignment does, is it makes copies. So it's really interesting, these return by reference functions can be used on both sides of the assignment operator. So typically a node class that didn't take advantage of return by reference would have two member functions for data, one to set the data and one to get the data. And two member functions for the link, one to get the link, one to set the link. If you do this return by reference, what you do is you merge those two guys into one more efficient function. There's no other reason to do this other than just pure slickness. Questions about that? All right. As I was grading, I think there are 5 in right now. There are probably more than 5 now. I've graded 5 of them. As I was grading, you may have noticed I asked for, I had an above and beyond category, and I totally forgot to mention above and beyond to you people. So a couple people that have had me before did above and beyond. People that haven't had me before have no idea what I'm even talking about. So typically when I make assignments, I ask you to give me some sort of small minor extension of the project that you thought up on your own, and I look for that. I expect that to be there and make it part of the grade. As I said, a couple of you did this for the linked list application. In the future, I will explicitly ask for above and beyond, and I will also ask for a comment for you to describe to me what above and beyond should be. That said, I will not be asking for an above and beyond on the stack program because
Come on.
it's a stack. I can't really think of anything.
2 elements at once.
Yeah. So that you will have ample opportunity to make up for this, however, next week when we will start using stacks. In fact, we're going to start talking about this on Friday. We'll start using stacks to parse expressions. For example, this is really cool. For example, you will write a program that can do
And you're just typing this in as a string?
Yeah, you're typing this in as a string, and it's going to start at the left-hand side and grab that parenthesis and grab that 2 and grab that plus sign and grab that 2, and it's going to give the right answer. Right? This thing is right. How do we do this? The things in the parentheses happen first. So this is 4 times 3 plus 9 minus 8 minus 4 is 4 divided by 2. And then what?
12 with that.
Multiplication happens before addition and subtraction, right? So we get 12 plus 9 minus 2. And then multiplication and division are tied in their precedence, as are addition and subtraction. They're tied in their precedence. In the case of ties, how does it work?
Left to right.
Left to right. So we do 12 plus 9, which is 21, minus 2, which is 19. That sounds really nightmarishly difficult, doesn't it? Yeah. It's actually astoundingly easy with a stack. So if you want to read ahead and see and see about this, it's in the readings from Gashard that I've assigned, section 3.1 from Gashard. And that's what we're going to work through. Now, there's going to be lots of opportunity. My default expression parser is really just going to be asking you to handle the 4 arithmetic operations, multiplication, division, addition, and subtraction. It's going to ask you to handle parentheses, and it's going to ask you to handle negation. What is negation? For example, we also want to be able to make sense of something like this.
Will we only be dealing with whole numbers?
No, we'll be dealing with doubles. It's not bad, I promise you. We will be using peek a lot.
Oh yeah.
So what you're going to do is you're going to peek out there and you see if there's a number coming in, and then you're going to read it in using C and double. And C and double just grab that whole double, and then you go peek and see if there's an operator out there or a number. And it's so you just constantly peeking out there and seeing what you need to read next. If you peek out there, sorry?
Those spaces, I'm guessing.
No, we'll have spaces, as many spaces as you want. You're going to have a little program, a little while loop that eats spaces for dinner. Right? So between every time you grab a token, you're going to go out there and look and see if there's an operator waiting to come in or a number. And if there's neither, you're going to eat characters until there's either an operator waiting to come in or a number.
So if people are writing random like sentences in the middle of their expression.
What if they want to do hex?
Now,
Shut up. This is hard.
so there's negation. And you're also, you know, your properly functioning program will be able to handle this. So nested parentheses
What if
or
there's only 3 parentheses on the right-hand side?
above and beyond opportunity.
All right.
Mismatched parentheses. Would you like to try again? So I'm going to be asking for just a finite collection, a simple collection of arithmetic operations, and parentheses you have to handle in negation. The opportunities for above and beyond are really quite extensive here. For example, I've had students implement the trig functions, the exponential functions, the log functions, which are not hard to do because they're already built into C++. It's just a matter of recognizing that S, if you hit an S, then you should start looking for an I and an N. And when you get the SIN, then you know you've got a sign operator that you want to push onto the stack. It gets a little dicey, I guess. Let me think. Are there any operators that start with the same letters?
Square root and sine.
Square root and sine. So now, square root and sine, you get the S, and now you know, oh, I've got a square root or a sine, and then you have to look at the next character to figure out which one it is. So parsing these things is, you begin to see why Maple sort of bitches at you so much, right? Because it's really tough to write a robust parser, and what you do instead is you require the user to adhere to certain syntactical conventions. That said, we'll start talking about this on Friday.
It's pretty impressive.
Don't forget,